Alright, this video is going to be on the squeeze theorem in calculus. And before we even get started seeing what the squeeze theorem is, I just want to go through this sample problem because I stole it from another teacher online. I thought it was really good. It's a good intro to what this is. So the first thing they want us to do is graph the function f of x equals x squared. So I know that when I graph that function, if I plug 0 in for x, then the y-coordinate is 0. If I plug 1 in for x, then the y-coordinate is 1. If I plug in -1 for x, then the y-coordinate is -1. To make a more accurate graph, I'm going to go ahead and plug in 1/2 and -1/2. So 1/2 is an x value. If I square it, that becomes 1/4. And -1/2 squared would also be 1/4. And then I'm just going to go ahead and sketch that. All right, and then I'm going to hang on a second before I graph g of x because that's kind of a crazy function. But -x squared I can also graph fairly easily. So that's just the same graph but flipped across the x-axis. So I'm going to go ahead and draw that. And before I do anything further, off to the side of the notes, I'm going to write down the limit as x approaches 0 for the function f of x. And let me not write the answer yet. Ooh, okay. That was a great erasing job. So let's say we're looking at the picture and we're asking ourselves, at x equals 0, what does it look like the y value should be? Well, it looks like the y value should be 0. And this is one of those easy cases because 0 as an x value is within the domain, and when you plug it in and evaluate it, there's an actual y-coordinate there, and that really is what the limit of the graph is. So that's kind of a simple example. Same thing for h of x. If you find the limit as x approaches 0 of h of x, you're also going to get 0. So those two are pretty simple. So what we want to do now is use our calculator to type in this equation right here. So this is what g of x is, and I went ahead and typed it. And it says to make sure that your calculator is in radian mode, so go ahead and hit the mode button. And we want to make sure that our calculator is dark, where it says radians. And then if you go ahead and hit the window button, I went ahead and made my window rather small so I could see what was going on, and because the window is pretty small on the paper. So if you want to set your calculator so it's at the same numbers that my calculator's at, then when you hit graph, you're able to see that that's the picture of the graph. And we looked at a picture similar to this when we talked about limits that didn't exist. And one of the limits that didn't exist was in a function that oscillates. And so here, we're going to have a hard time finding the limit of this function. So if you go back and we're looking at the limit of this and we say, what's the limit as x approaches 0? It's undefined because 1 divided by 0 is not something that we can evaluate. We can't plug in quotes of 1 divided by 0. So we know that that this is undefined at that point. We know that. We just don't know, and we know it's not a whole because we don't have factors canceling, so it's kind of hard to find the limit for this. So what we're going to do is we're going to take this picture and we're going to add it to the picture that we've already drawn. And to do that, I went ahead and I hit the trace button. And now I can kind of look at my cursor and scroll back and forth and see what the numbers are, just as a means of helping me to maybe graph it a little bit more accurately. So I can see that at -1, the y-coordinate is a little bit above 0.5. And I can see that down here at this lowest point, you know, that the x-coordinate is about -0.7 and the y-coordinate is a little bit less than 0.5. And then from there, I can just see that it kind of does that zigzag. It does that oscillation right there. Lots of bouncing around. So I'm going to go ahead and just draw something. It doesn't have to be super accurate. You get the idea of what it's doing. It's bouncing back and forth. something like that. Now, if you look at this picture, you can kind of see that this oscillating function in here is like, it's like being squeezed between those other two functions. And so if you know that the other two functions, the limit as x approaches 0 for each of those, it would make sense that the limit for this function is going to be 0 as well as x approaches 0, just because the entire function falls in between those, so why not? So I'm going to write a little note to myself. I'm going to say the y value that appears to be there is 0. And so that's just me writing a note to myself, because I remember that when we said in plain language what a limit was, it was, you know, the y value that seemed like it should fit, or the y value that appears to be there. Okay, so the squeeze theorem. Hang on, gotta look at my notes. The squeeze theorem states that if f of x and h of x are like the top and the bottom function, so you can see on your notes these are not in different colors, but on my notes they are. So if you want to pause the video and put them in color, that could be helpful. So if you have two functions that are like above and below another function, and you have the other function squeezed in between them, when x is near c, so go ahead down here, this is a typo, this should be a c right there. When x is near c, except possibly at c, we'll get to that later, and the limit as x approaches c of f of x equals the limit as x approaches c of h of x. So this is exactly the same situation we were talking about up here. So the limit as x went to 0 for the top parabola and the bottom parabola was 0 for both of those. So if the limit for these two things is the same at the point c, then we're going to say the limit as x goes to c of g of x is also the same. So I'm going to say that these equal some limit L. They equal each other and they equal some limit L. Then we can say that that limit is the same for this one as well. All right. So what I would like for you to do is pause the video and take a moment and maybe write down in your own words what the theorem seems to mean. Why does it make sense? Write it in some plain language, because this is a really mathy way of phrasing it. You can refer to the picture, you can draw arrows, you can do whatever you need to do. But go ahead and pause and take a moment to write a good explanation of why that makes sense. All right, so now what we're going to do is focus on the back side of the sheet of paper. So here we're going to do the squeeze theorem in practice. And so if you remember when we were looking at those pictures, what we noticed is if the limit of the bottom function was the same as the limit of the top function at that point, and we had something that was in between them, then we could assume that that thing that was in between them had the same limit. So for us to figure out what the limit of f of x is, we don't even know what the function is, but for us to find the limit of it, we're going to take the two functions that are below it and the function above it, and we're going to check those limits and see what they are. And that will allow us to come to our conclusion. So when I do the limit as x approaches -1 of x minus 3, I can do direct substitution here because -1 is in the domain. So I plug -1 in and I get -4. All right, and I'm going to do the same thing with that other function. The limit as x approaches -1 of x squared plus 3x minus 2. And if I plug that in, -1 squared is +1. 3 times -1 is -3. So I have 1, take away 3, take away 2, that is also -4. So because of the squeeze theorem, because I know that f of x as a function, that the y values for f of x fall between the y values for x minus 3 and between the y values for x squared plus 3x minus 2, because I know that is the case, then I'm going to say the limit as x approaches -1 of the function f of x equals -4 as well. All right, now here is kind of the nifty part of the squeeze theorem. And so this The squeeze theorem is really where we start to evaluate limits at trig functions. So for this one, we have a lot going on here, but where I'm going to start is I'm going to say that I know that sine x is between -1 and +1. And this goes back to me talking to you guys about that video, that whenever we take sine of a number, that number is a reference angle in a triangle. So this is sine of some angle measurement. And sine of an angle measurement equals a ratio. And the ratio is constructed as opposite over hypotenuse. So that means that the ratio is always between -1 and 1. However you write it, that ratio, that number for sine, when you evaluate it, always going to be between -1 and 1. So right here, I am putting a sandwich together. I am making something that I can squeeze so that I can evaluate this problem. Now, we normally say sine of x. It doesn't matter if it's just x that we're evaluating. Anything that we plug into sine is going to have this property. So I'm going to go ahead and rewrite this so it fits our problem a little bit better. I'm going to say that we're finding sine of x squared, of 1 over x squared plus 1. And I know that whatever I happen to plug into a sine function, no matter what I do, I'm always going to have it between a ratio of -1 and +1, because the ratio is opposite over hypotenuse. So now I need to be able to sandwich this exact function. This is the function that needs to be sandwiched. I need to have that somehow in the middle of two other functions. And right now I'm pretty close to this function, but I'm not quite there. So what I'm going to do, I'm going to take x to the 4th and I'm going to multiply it by all three of these pieces. So I've got -x to the 4th, and then x to the 4th sine of 1 over x squared plus 1, and then x to the 4th over here. So now if you can see this, I've created this sandwich right here where I've got the function that I'm looking for in between, and this, if you looked at it, this would be an oscillating function. It's not something that you can plug 0 into. It would be undefined. We would have issues if we did that. So here we can evaluate the ends separately, the bottom of the picture, the top of the picture, and see if what's in between should have the same limit or not, or if it's maybe something that we can't find. So I'm going to say the limit as x approaches 0 of -x to the 4th is 0. And the limit as x approaches 0 of positive x to the 4th would also be 0 if I plugged it in. And so because the bottom and the top agree with each other, then I can make the conclusion that as x approaches 0 of this whole function right here, the limit should be 0. And I can make that conclusion by the squeeze theorem. All right, these examples are going to start to get a little bit crazy. So here we are evaluating this limit at infinity. And that's a little bit confusing because how do you plug in cos infinity? How do you plug in infinity plus 2? So what we're going to go ahead and do is we're just going to do the squeeze theorem to evaluate this. There's actually other ways to evaluate it, but we're going to use the squeeze theorem because it's the instructions and because it's the context of what we're learning. So I'm going to go ahead and start just by saying that I know that cos of x is in between +1 and -1. I'm going to start there. I know that the ratio there is adjacent over hypotenuse, and so that's a conclusion that I can make. Now my goal is to start to do things to make it so this middle function looks more and more and more like this problem right here. And so an easy thing for me to start with would be to take that inequality and multiply the entire inequality by -1, because this is a negative cos right here. So that's going to give me +1, that's going to give me negative cos x, and that's going to give me a -1 over here. And if you guys recall from back in the day, anytime you multiply or divide an inequality by a negative number, you have to switch the inequality symbols. So I'm going to go ahead and switch the direction. So that just means that this number is the bottom of the function now, and this number is the top of the function. All right, so again, I'm going to get closer and closer to my middle function actually equaling this. And so to do that, I need to have a 3 that goes with that negative cos x. So I'm going to go ahead and add 3 here, add 3 here, add 3 here. All right, so if I do 1 plus 3, that gives me 4. If I have negative cos x and I add 3 to it, I'll go ahead and put it in the front so it looks the same. It would look like that. And negative 1, if you add 3 to that, you get 2. All right. Next, I have one final step to make this look the same as the middle function. So I want to go through and I want to divide each of these pieces by x plus 2. So I'm going to have 4 divided by x plus 2. I'm going to have 3 minus cos x divided by x plus 2. And I'm going to have 2 divided by x plus 2. And you'll notice I have not put the symbols yet. And the reason I haven't put the symbols yet is because I have to consider, I just divided by x plus 2. I have to consider whether or not that thing I divided by is positive or negative. Because if it was negative, I got to flip my symbols. And if it was positive, I'm going to keep them the same. So if we consider what we're plugging in, we're about to plug in a positive infinity. And positive infinity plus 2 is going to end up being a positive number. So that means we just divided by a positive number. And so our inequality symbols are going to stay in the same direction. They don't need to change. All right, so now I can do the squeeze theorem. Now I can start to plug in infinities and see what I get. So if I say the limit as x goes to infinity of 4 over x plus 2, then we know if I plug infinity in here, I have a little number 4 divided by a huge number, and that is 0. And then if I do the limit as x goes to infinity of 2 over x plus 2, I'm going to arrive at the same conclusion. So if I plug infinity there, I get 2 over an enormous number. That's approximately 0. And so that means that by the squeeze theorem, I can conclude that as x approaches infinity of this function, the limit is 0.